Hello, this is Mr. Waters, and I'm going to do another example from the homework, this time on page 680, and this was an example dealing with projectile motion and parametric equations. In this particular problem, as you can see, we're going to have Wanda throwing a ball straight up into the air, with an initial speed of 100 feet per second. Okay, what are we supposed to do with this? Well, we're supposed to find the parametric equations that describe its motion. We're supposed to calculate how long the ball is on the air and when, that is, at what time the ball is at its maximum height, and then we're supposed to determine the height of the ball. Okay, and those three pieces, B and C, we're going to calculate those based on A. Well, we know from physics that those two equations are the formula that determine projectile motion for an object under gravity. Okay, and they've got, as you can see, some constants in there. Okay, V naught is the initial speed, theta is the initial angle, G is Earth's gravity, or whatever the gravity is that's exerting on the ball. Could be the moon, could be Jupiter. There's V naught again, the initial speed. There's theta again, that's sine theta this time. H is the initial height. So over here, so we can kind of gather all the information needed, we're going to say V naught, that's the initial speed, that's given as 100 feet per second. And notice that the information here is given in imperial units. Theta is the initial angle. Well, you can see that if Wanda's ball, her throw is straight up like that, then that means that the initial angle is 90 degrees, the angle with the horizontal. So that's going to be 90 degrees. Okay. G, Earth's gravity, in imperial units is 32 feet per second squared. And the initial height, the simplification here is that since it's close to the ground, we're going to say that the initial height is equal to 0. Okay, so anyway, so in order to get the parametric equations here, all we're going to do is we're going to substitute the information, the constants we're given, into the equations. Okay, so x is going to be equal to 100 times cosine 90 degrees times t. Y is equal to negative 1/2 times 32 t squared plus 100, the initial speed again, sine 90 degrees t plus 0, because that's the initial height. Okay, well, cosine of 90, as we remember, is equal to 0. So that's going to be 100 times 0 times t, which of course is equal to 0. And then negative 1/2 times 32 is negative 16 t squared. Sine of 90 is 1, so 100 times 1 is 100 t, and then plus 0, we can leave that off. So those are our two parametric equations. X is equal to 0, which really we don't even need to write. It's not too surprising. That means that there's no horizontal component of motion, which clearly that's true because she's throwing the ball straight up into the air. There's no horizontal motion at all. So this is negative 16 t squared plus 100 t, and those are our two parametric equations. Now, we're going to use those to calculate how long the ball is in the air. Well, if you think about it, Wanda's here, and she throws the ball straight up, and it comes back down. Okay? Well, when the ball comes back down, which is at the end of its time in the air, its height is equal to 0. And in fact, as you can see, really the ball is at 0 height twice. Once right at time equals 0 when it's starting out, and then at the instant that it comes back down again. So to find how long it's in the air is between those two points, And so to find the time in the air, we're going to set y in the equations equal to 0. So scroll down a little bit. So here is b. So we're going to use, we don't care about the horizontal motion because it's 0. So y equal to 0, you understand. So negative 16t squared plus 100t is equal to 0. Now you can see that's just a quadratic equation, and conveniently enough, both terms have got that constant factor t. So we're going to go ahead and factor the t out, leaving on the inside negative 16t plus 100 equals to 0, like that. Okay. So that gives us our two sub-equations. I'll put them over here. T is equal to 0, which is right. That's when it's first on the ground. And then negative 16t, or negative 16t plus 100 is equal to 0. Okay, we'll subtract 100 from both sides and get negative t is equal to negative 100. Divide both sides by negative 16, and I'm getting, on my calculator, 100 divided by 16, that's 6.25. So the ball is in the air for 6.25 seconds. So that is the answer to B, how long is the ball in the air. Now, we get to C, and if you'll recall, scrolling back up, when is the ball at its maximum height, and we want to determine the maximum height. Well, okay, one way of looking at that, since it's straight up and straight down, the ball is going to be, I'll put it over here, at its maximum height halfway through its travel. Okay, so if it travels for 6.25 seconds, okay, the height at the top there, the vertex of its travel, is going to be 1/2 of that. So it's going to be 6.25 divided by 2, which according to my calculator is 3.125. So the seconds. Okay, so the max, so time to reach max height is equal to 3.125. Now, you can also see that as a kind of very long, skinny parabola, and so we could have used the vertex formula too. Opposite b over 2a would give us the same thing, but we'll use that later on. For a straight up and down trip like that, it's maybe simpler to see it's just half the height, or rather half the time. Now the second part is, what's the height? How high is it at that point, h? Well, that's the height in our equation up here that corresponds to the maximum height time of 3.125. So I'm going to put the h of, we're calculating h of, or rather, well, y of 3.125 is equal to negative 16 times 3.125 squared plus 100 times 3.125. Okay, well, 3.125 times negative 16, that's convenient, that's 3.125 squared, isn't it? So it's going to be 3.125 squared times negative 16, and I'm getting negative 156.8 3.125, right, plus 100 times 3.125, so that's plus 312.5. So we add those together, and we get 156.25 feet. So that is the max height, which corresponds to the time. And so there is the other answer for C. So here is the amount of time that it takes to reach its max height, and that is its maximum height there. Okay, thanks for listening. Now I'm going to do a part B of this video in which we use some other angle besides straight up and down, and that's to give us a slightly more complicated example. So if you want to listen to that one, listen to part B. Thanks for listening.